Hello. Thank you. So because this presentation was originally planned for 1 hour, I had to compress stuff and do some tricks. And these tricks work at best when you actually prepare also for yourself by probably opening that link that I put there on the screen to actually be able to follow that, because at the beginning the light was not that ideal, and so looking at that screen was not that perfect experience. So however, let's start. So there's a lot of talk about DeepSpeech recently, and I just want to present here more like a user's and developer's perspective, not that much machine learners and scientists' perspective, more like what the outcome of that is and what contributors can do to help us. So to start here, first this simple question like, what are we actually doing? So what we do is that we develop a speech-to-text system. That means this is this little component. Well, little is probably a bad word for that. It's actually quite a powerful component that enables voice assistants, like for example Cortana, Siri, and Alexa Echo, and so forth. And this is that piece that translates audio, raw audio data, into text. So these assistants need more components than that, for example like voice activity detection and the reverse operation like creating a voice from text. But at the moment we concentrate on this actual hard part of translating speech into text. This is based actually on TensorFlow, and those of you who know, this is actually a Python-based framework developed by Google, and we built DeepSpeech actually following a paper from Baidu that's actually quite famous, and we just realized what's in that paper in TensorFlow to make it accessible for everybody. So why are we doing this? That's actually, I want to answer this threefold. So, because it's a typical, it's a nice thing to do like that. So first thing is, we actually want to have a state-of-the-art solution that's not proprietary. So state-of-the-art means there's this classical approaches that are based on hidden Markov models and so forth, and that are very manually driven, programmed literally from end to end. Every piece of that solution is programmed by people. And what we wanted to do is to have this state-of-the-art solutions like Google and others do, and have this actually available for the broader public and not just for proprietary players. And we know that this is typically proprietary solutions tend to get evil at some point. So, and therefore, we try to get a better solution here. So the second reason is that we actually want to have offline support. So as you probably know, most assistants nowadays actually are based on this schema of having some audio data recorded locally, sent over the network, translated on some server, sent back. And this comes with many drawbacks. And most importantly, our approach of offline support would solve this privacy issue that this has actually inherently. And secondly, this will also lead to lower latency. And if you have, if you really experience the solutions nowadays, even small improvements in latency actually are really recognizable. You actually get a different and better feeling of the solution And the third reason is that an end-to-end machine learning approach, namely not coding everything from A to Z, but actually having machine learning filling the gap from input to output more or less automatically, is better in scaling. That means if you have data from, let me say, an unknown language X, and you have enough data of it, you would not have to start coding actually based on a linguistic pattern a new solution, but you would instead just train the system to learn this language by itself, more or less. And the second thing is also that you have a better degree of quality. And that means these end-to-end machine learning solutions are better at actually accessing that details in the abstraction levels that you typically have in that systems in a way that is actually more powerful for the outcome, that is actually leading to greater quality. So it's actually also in quality scaling better. So I actually, as I said already, like want to give a bit like a user's perspective. And first thing I want to say, like we released. Means like it was a bit like a silent release, but in the end we released, and this was actually a couple of weeks ago, like it was last year. And this week actually we had already a secondary release, like, and I actually want to show you what's in the package. So first thing is how you prepare the environment. Like we have software packages that you can just install, but for them to work, you need the data, namely the models, the brain, you could say, like that we train. You have to download it and you have to get it somewhere. And this is what I actually now want to show you. It's a bit like accelerated. I'm not able to type that fast, I have to admit. So first you actually get the models downloaded. It's actually a huge package that we provide on GitHub. Then you actually download also some audio data. And you can see here, like the audio data is actually provided for you for demo purposes, for testing, simple tests. And I would now like to try to play one of these samples that I use throughout this demo now. This is that 8455XYZ sample. And I will go with the microphone near to my notebook. Wow. So it's actually somebody telling, so saying like your power is sufficient as said. So like, I do not want to lose too many words on that, but the thing is, now I want to show you like how this actually works in Python to understand this sentence. So like, you first create a virtual environment, and this is really like from scratch. Like you create a virtual environment, you source it, then you actually do pip install of DeepSpeech. And it comes batteries included, namely it has a command line tool, as you can see here, with usage parameters. And now actually we just pass in the model that we downloaded, the WAV file that I just played, and the alphabet. And you can see here how it was translated actually into that sentence that I just showed you. And the same happens here in a second pass with a GPU-powered solution. As you can see, like the GPU one is actually faster. And this is what we currently also concentrate on to get the solution faster in regards to real time. Like, you have a certain computing overhead that this model actually implies, and at the moment, if you go with a CPU there, we are almost around real time on a normal PC. With a GPU, you will get more. So like you can see that from the interpretation times that you can see here in the log. So it's a simplified representation of this code. It's actually really like simple. You have an import, you do then a model, you create a model, then you enable the decoder with a language model, and you pass in pretty much that what I passed into this command line utility, and then in the end you print the transcript. So there's also a Node.js version of this. It's very, very similar. You actually also can just use npm install DeepSpeech. Well, the typical kind of like npm workflow here. It warns you here now on not an uninitialized project. And then you can actually here use the client that comes also shipped with it, with the model again, with the audio again, and with the alphabet again, and you actually will get the translation. Same with the version on GPU basis. You just replace in the former statement, you will see in a second, you replace DeepSpeech with DeepSpeech-GPU, and you get actually the faster result. This is a bit like similar code, completely asynchronous, like Node is typically doing things. By the way, our community also provided already Rust and Go bindings, so you can just also work with Rust and Go on that. Some word to the performance in regards to quality. There is a kind of like a measurement that's called word error rate. Word error rate means like how many errors you have on how many correct words. There is typically done a measurement. There is some table in the net. that compares the different solutions against each other. However, part of this table is also from the DeepSpeech paper from Baidu. They measured the human performance, so like they actually let humans do the test, and to have some baseline to compare with. And the system that we currently have and the model that we actually provide for download is already actually performing better than humans. Just to get some comparability here. So now to more kind of like development centric view onto all of that, not embedding stuff, but really like using that stuff and extending it, namely training models and development. So like when you want to train a model, you have to have also done some preparation work. I show that here. This is primarily actually about, you have to, by the way, this is one of the most often questions in our forums and so forth, like, why isn't the download working? It's because Git LFS is not installed. So you have to install Git LFS first. So like when you actually clone our project, there's 3 steps that you have to do afterwards. The first step is actually to install the requirements, the Python requirements. There's a requirements txt file. And so like you can see that here. So we activate the environment that we just created. We install the requirements. And then after the requirements got installed, I install manually. This is actually an additional step you have to do when you have a GPU on your machine. You can additionally to the DeepSpeech package actually install also the requirements for a GPU, so the TensorFlow GPU support. We have a tool for that is actually integrating for all sorts of platforms the binaries that are required for that. Like this tool that you can see here is actually automatically downloading that in regards to your local machine. So yeah, and you have a tremendous amount of parameters. You can see here just the tail of the whole parameter bulk that DeepSpeech.py has as a command. And we actually, because this is so complicated, we want to later do an example that really like goes end to end through the whole process of using it. So first we need to get some data, and the data we actually gather together onto a page that we use. This is voice.mozilla.org/data, and we not only provide our common voice data, which is a corpus that we actually provide, but we link also to other data sources. So it's really like a one-stop shop here for actually getting actual data. I have to say this is only for the English language at the moment. Like this is English language corpora that are used for training that kind of deep speech models. So if you want to contribute your own voice, you can do that. There's a mask for that. You can actually just tap this button, and then it will actually start a recording process, and then you can contribute actually your voice by reading a sentence that's presented to you. And this is the way how we build up our own common voice corpus. It's free to be used by everybody in a sense, probably important to say. Like it's not just like that we get this data, then it's really like completely open data. And here you can see also like it's not just recording stuff, but also like verifying things. Like if something got recorded, it needs also to be verified by independent people. And there's some statistics process running in the background that says like if you have more positive votes than negative votes or no negative votes at all, then it's actually already validated as a valid file. Somebody had not been just like accidentally hitting record and recorded his cat in the background or whatsoever. So this is how that works. So you can install easily this common voice corpus. We have batteries included in DeepSpeech. We provide actually an own importer tool for that. This is, again, like sourcing our environment. And then we actually go into the bin, import CV. And this is really like just downloading everything. This actually, what you saw here is super, super accelerated. Like it takes really a long time to do. Like, and therefore I had to fake all of this. Like, so you can see here actually in the last command, that we have all sorts of CSV files. We will look into those CSV files later. But take a look at the different names that we have here. We have typically 3 different, in this case, suffixes. And one suffix is def and train and def, train, and test. And I will come later to that. So now I will give you a micro tutorial, actually end-to-end, how to use all of this. First, a bit of terminology. So loss is actually a name from the machine learning, and this is like indicating like as a number how different the actual outcome is from the expected outcome. So like if you have a translation of some audio into text, and you compare the textual outcome that you expect with the textual outcome that it computed, you will get a number. And that number is actually important for the system to actually do backpropagation in the process of learning. Sets in the data corpus, as we already saw, the data that's in the train set is used for training. The def set is in every application of the training data used for validating that we are still learning and not overfitting. We will come to that later. And the test set is in the end an unbiased set that is executed after the learning is completely done. You actually do a final test, and this is typically used for comparing across the industry the different systems. Because all of those tests are actually fixed by the ones who create the corpus. Not by the machine learners that actually use it, but by that people that actually provide the corpus. So that across the industry you can then compare solutions. An epoch is actually when you trained the whole training set one time. But actually typically in training what you do is you apply it several times, over and over and over again. So, and this is actually what we will do now in a second. We will try to overfit. That means like this is just a hello world demo in machine learning. It's not actual training. Overfitting means like you learn your training set. It means like it will only understand your training set. It will not learn a general understanding of the language. And this is because I have just one sample. I will show you that sample in a second. So in the end, when the validation set, the orange one, starts the loss starts to increase again and not decrease in the beginning of the training, it starts to increase again, you actually failed already. But we do that on purpose to just show that training works. So what I will show you now is actually not realistic in regards to creating a real model. It's just a fake. So like, and by the way, we have 2 different models. So like we have an acoustic and a language model. The acoustic one is that one that we train now. This is actually mapping sounds to letters. It's very simplified, but that's more or less what it does. And the latter one, the language model, is more or less, probably you remember typing support on mobile phones. Like it understands, on a stochastic point of view, it understands language and can correct kind of like literally translated audio into characters into actual written words. It just understands language on an orthographic point of view. And this is the terminology that we need. So first, we actually start to try to actually, I can really like now just read it. I recorded myself saying, Typograf Jakob Zürn schweißgequält vom öden Text. This is a stupid German sentence. That is a pangram. Pangram is every letter of the German language is at least one time in this sentence. It's like the quick fox jumps over and so forth, just for German. Now we create a corpus from that sample. Oops. This. And this is really simple. It's in the end just like we have the sample. We make a corpus directory. In that directory, a WAV file directory. We move the WAV file there. Then we actually create one of these, in this case, a train1 CSV file. The CSV file consists of 3 columns, a file name. This is actually an absolute file name, namely it needs to be rooted. Then the WAV file size and the transcript. And I enter really like the absolute path now of this Jacob WAV file, the file size of that I just remembered, and write down this stupid sentence, lowercase because it's not required to be different in casing because you don't hear casing. It's just like the system will translate case insensitive. From there on, we now create a language model. This is a bit more tricky. For that, I actually used a Gutenberg book, a German Gutenberg book, that I just downloaded, and that I actually use with a tool called CanLM. This is that tool that is used for language models typically, and you can see here like how this is used. You just passed in that text in a sense, and you get this kind of language model automatically. So there's no training in the sense, like it's more like a conversion. And you can see here, I am now doing a German alphabet. I remove this apostrophe that is not used in German. I add instead the Umlaute, Ä, Ö, Ü, and SZ, and that's pretty much it. Then downloading the Gutenberg book. You can see here, like it's simplified, it's lowercase, all sentences are actually on separate lines. And then actually we create, using CanLM, this model. There's a need to convert it also to a binary representation that is cheaper in space. And then last not least, we create a so-called tree file that is used by our piece of software. That's not the language model, but the acoustic model for connecting to the language model. Now let's do the almost last step. Altogether, it's always a good thing to write a so-called .run script. .run is actually git ignored in the root of our DeepSpeech project, so you can just put in your own .run, and that is actually parameterizing DeepSpeech to your own needs. So you put in this case, this simplified one sample corpus that I just created 3 times for development, test, and validation. So like for not development, for training, test, and validation. And the link to the alphabet file that we created, to this language model, the tree and the binary paths that we just created. I actually measured or figured out the hyperparameters, learning rate, and dropout rate. This is in machine learning called hyperparameters. I had to try out like what the best values are for my purpose for the demo here. And the rest is more like clutter, except for the last one. This is actually then here specifying this directory German models. Actually, as the export directory, once it actually got trained, it will store the model there, and we will have actually a similar directory to the English one that we provide. So this is, whoops, this is like a real-time view now of the training process. This is not accelerated. This is also me typing slow, by the way. So and you will see, like, he first complains about, oh no, validation step needs to be bigger than 0 for early stopping to work. This is just like me doing overfitting stuff without carrying on validation at all. But you can see here he's starting optimization, and the first thing that he learns is something, and something. And then he's shortening it in to just one letter and goes on like that. And you can see here, if you look at the loss, if you spot the loss, it's going down over the steps. But this is boring to look at that because this will take a while. So I actually prepared a 20-time accelerated version of this. And this looks like this. And now look how the sentence on the bottom converts over time as the network understands what that means. Except for this Öden, which is, by the way, I can stop. This Öden is a German word and DEN is a German word. And the problem is DEN is matching better here. And therefore he actually all the time wants to match DEN, but he will get it. At some point he will get it, and then he will not list these entries anymore because he is only listing stuff that's failing. Here already he matched it. So it means, like, you can see we trained in an overfitting fashion perfectly this one sentence. This model is understanding only in just this one sentence and not a general German representation. And you can see here now in the German models folder, it's actually also, if you see that output graph PB, we already have the kind of like similar directory that we ship for English by our release of DeepSpeech. Next steps for you, actually, if you want to go for doing something more serious on that, is to get more transcribed voice data, get more in contemporary language model texts. The texts from Gutenberg are not contemporary German. So like it's not matching certain things. It's really not working for modern German, you could say. Like it's similar for any other language where you do not have really like contemporary text. You have to tune the hyperparameters for a real scenario, not for this overfitting stupid stuff that I demoed here. And you have to get hardware because machine learning is computing intensive as hell. We use 2 machines with 8 Titan X Pascal cards in it for 2 weeks to train the model for English that we ship. And spread the word. So last not least, our roadmap for 2018 is to train for another language, not named yet, to have streaming support. This is like that the computing starts already when the first samples come in, not just when the recording is done and then you pass it into the machinery, so you lose some time. Optimizing for noisy backgrounds. This is really like having samples augmented with street noise, restaurant noise, stuff like that, actually barking dogs in the background, kitchen backgrounds, and so forth. So to actually make it capable of understanding language also under that conditions. And in the end, we are currently working also on text-to-speech. So we want to actually also have a text-to-speech component. So like, you can talk to us. We are on IRC. We are the machine learning group. And that is actually our discourse. So please feel free to contact us. That's it.